There we go. All right. And can you see the full slides now? Cool. So I'll preface this with one sort of logistical note, which is that foolishly, I might have to let someone into the building in 15 minutes. I tried to organize to get someone else to take care of that, but it'll be very natural if I just sort of get interrupted all of a sudden. So hopefully that's charming. Yeah, so I've labeled this a journey with Tim Dobbs. Because basically, I don't think I'm an expert on embedded systems and C++, um, but I've learned a ton in the past year just because I kind of had to. For work, a little context, I've been working at this company for the past year or so, building bioreactors, and we're building the embedded systems that drive those bioreactors on top of everything else. So I thought I would take today and just sort of share some of the things I've learned. I think this can be pretty conversational. I'm sure some of you actually know things I don't. So, feel free to sort of, stop and say, oh, have you thought about this? Or, here's an extra idea that you didn't cover. But this is just generally like a bunch of stuff that I wish I had had in a slide deck about a year ago, because I think it would have kickstarted me faster. And it's really neat. I've been really enjoying the sort of working in embedded systems world. So let's move ahead. So what's an embedded system? I mean, it's a vague concept, but essentially it's a self-contained sort of computing module. The idea is that this thing performs a specific task. So the thing that I keep coming back to is something like a Fitbit, where it's like, oh, it's a small little device that has to have some computation in it, but it's not like a full computer. Embedded systems are everywhere. So, they also drive things like, yeah, I don't know. I mean, your PCR machine has an embedded system inside of it. Your microwave has an embedded system inside of it. Basically, the idea is that this is not a full computer, but it is something that needs some computational power. Um, and in my case, I was interested in working with these because what they're really good at is, do you need something that's going to actuate a mechanical part, something that like will interact with the world? Um, they're also really good at working in the field because they do like one thing, they can be really reliable. And also like, yeah, so you can get, a small rugged piece of on a printed circuit board, and like put that out into, a farm to measure the moisture in the soil or something. And that would work, whereas putting a laptop out there wouldn't. And then same for long-term reliability. You can just say, okay, I'm going to send that away for years. It's just going to do one thing well forever. Um, Additionally, a lot of times embedded systems have real-time computing restraints, which is to say that like when things happen matters. It's not just like, send me the document when you get a chance. It's like, oh, well, is the microwave has to start now as soon as someone presses a button, and then the microwave ticks for a certain amount of time and then ends. Um, and then additionally, a lot of computers are good with networking with other devices, but embedded systems, that's particularly important because usually you want some degree of interaction with the greater world that's not just this one thing that does something well. So a couple of examples on that. So thinking about like those things that they're good at, you might think of, well, environmental monitoring is a classic use case here, where it's just, I want to just measure the wind speed forever. Same thing with wearables. So I mentioned a Fitbit earlier. And if you have anything where you're like, I just need to measure something reliably and I don't want to like strap a Raspberry Pi to my chest, you can imagine getting a tiny little processor and fitting it in there. PCR I mentioned, auto sampling devices, time-lapse devices. It's sort of a classic use case for this because they just sit and hum along and do their thing. So, oh, I just need to take one photo every 5 minutes, every hour. Well, yeah, you don't really need a MacBook Pro for that. And then, of course, in my use case, bioreactors is another use case of something where I just want this thing to do something regularly. Okay, so what like is that though? Like, because I just mentioned embedded systems. So I'm throwing out a couple of ideas. Some, you've probably heard of. I'm not sure how well versed everyone here is in sort of like boards you can buy, but surely you've heard of Arduinos. So Arduinos is the general thing we're talking about here, but there's a whole world inside of that. So Arduino got really popular over the past 20 years or so because they made a lot of stuff really easy to program these embedded systems. and then they built sort of an ecosystem around it. So I'm sure you guys have had the experience of like, all right, maybe I'll just pick up an Arduino for $20 and I don't know, maybe I can code up something fun this weekend. So that's kind of what Arduino has made possible. And then there's a world, if you keep going deeper than that, all the way down to I'm buying something directly from one of the biofabs, or not biofabs. We're in biology, so but yeah, the circuit fabs. And um and then just using one of those. So anyway, just to sort of put some grounding underneath it, here's 4 boards. So the Arduino Maker is pretty popular in the sort of embedded systems world. You can see it's pretty small. I don't have any kind of banana for scale or anything here, but these guys are an inch or two, less than an inch really, or less than 2 inches. And what I've learned about working with these is that they are really easy to use because you have the Arduino community kind of behind it. You have the whole ecosystem. They sell little shields that you can just sort of plug the next thing into it. So if you need like an additional piece of hardware, you can just sort of plug it on top. And then these are running on, I've learned that the processor type ends up being kind of one of the most important things. So this is running on a SAMD21, which is a processor from ARM, which seems to have pretty good support. And then you've got the Raspberry Pi Pico. This came out pretty recently. I bought one of these and never actually got to use it, but I am kind of excited about it because it's I like the Raspberry Pi Foundation. I like the way they document things. And also, interestingly, so most of these, what you'll do to program them is you'll write probably C++ code and then compile that down into an instruction set for the processor. But the Raspberry Pi Pico can also run MicroPython, which I haven't played around with, but sounds kind of interesting. So you can, write something that's a little more Python-like if you're comfortable with that, and then just like run that into the board. Plus, you get the Raspberry Pi community for that one, and they have really good documentation. And that's running on this RP2040. So the Raspberry Pi Foundation made their own processor, but it's also based on the ARM Cortex M0 Plus, I think is what it's called. But basically, the SAMD21 and the RP2040 are based on the same sort of base processor, so they should have pretty similar functionality. And then these two on the bottom, I like the SparkFun IoT Red board for prototyping because it just has lots and lots of you can see it's bigger than the other ones. So you have lots of ports and you can sort of play around with ideas that you need there. And that's based on the ESP32. ESP32 is one of the most widely used processors for like professional IoT stuff. So IoT is Internet of Things, which is just a buzzword that's about like, oh, how do I make little objects that can then connect to the internet? So I like the ESP32. That's from a company called Expressive, and they do this really cool thing where actually it's 2 processors, and one of them is in charge of keeping Wi-Fi connected. So these things out of the box have good Wi-Fi, which is really nice. And then another opportunity to use the ESP32 is this Adafruit Feather V2. That's really nice because it's much smaller, so you get a really small footprint, and you can kind of like integrate that more tightly into whatever package you want. So that's just a few boards. So at this stage, if you're like me, you may be saying, I don't know. I mean, I can kind of program a Raspberry Pi just fine, and they're not that much more expensive. Maybe you could just use that. Well, a microcontroller can be a couple dollars total. So it can be a lot cheaper, especially I haven't tried to buy a Raspberry Pi in the past few months, but last time I tried to buy them, they were like hundreds of dollars because of chip shortages. But generally, Raspberry Pi is more of a single board computer rather than just a microcontroller. And what that means is that it kind of comes with this whole peripheral set that we're used to in desktop computing. So it's nice because you get all the tools that you have on Linux, or you can run other operating systems on a Raspberry Pi. And that's really cool if you're used to that ecosystem. The downside of that is, of course, you can get all the errors you can get on Linux as well. There's just additional complexity to running an entire operating system on a board. And you may see problems that you wouldn't see otherwise if you just sort of said, okay, all this device does is turn on a light every 10 seconds. The other nice thing is you get the standard computer peripherals. So Raspberry Pi, of course, has USB and network connections and an HDMI port. and you get GPIO, which is general purpose input output. And so that is really nice because Raspberry Pi still can actuate things. Like, it's not a bad choice for a lot of automation solutions. Um, the microcontroller, on the other hand, you basically directly program the processor. Like I said, you compile all of the code you wrote down for that processor, and then that's what that does. It turns on and it starts running your code, and it doesn't do anything else. Um, the downside of that is you do have to bring your own peripherals, so that can be good and bad. So if you want like other stuff to interact with your microcontroller, then um, you'll need to figure out how to wire that together. So that's bad if what you needed was a USB port and excuse me, and you don't have one. Um, but it's good in that, well, great, you get to make the thing you want to make. So if you're kind of starting from scratch, this is a really nice way to like make an object that does the thing you need exactly. The other thing about microcontrollers is because they do so much less computing, it's a really small footprint typically and low power. So that's nice. Um, so yeah, so coming back to our sort of example applications, you can see how a microcontroller is probably a good fit for most of these. The bioreactor, actually you can imagine, well, I don't know, that is sort of, it has a screen. It is kind of starting to act like a computer. Maybe that actually is a Raspberry Pi application. So there's just sort of a gray area there. So this is how I've come to think of it. Kind of conceptualize this idea of a compute object, which is like a physical thing that has both logical and physical interactions with the world. So it's like, a thing I can pick up and touch and move around, but at the same time, I need it to follow some rules that I can program into it. And so kind of how I've started to think of it is like, okay, well, a microcontroller is when you would make a compute object. Whereas if you want if your main concern is just the logic and like, yeah, it could maybe do some physical stuff, that's more of a fit for a computer, whether that be a server or a single board computer, or lots of ideas around there. So that's kind of how I've come to think of it. Great. And then so that's kind of an overview. I don't know, any questions at that point? Otherwise, I'll jump into just like, oh, here's some cool stuff that I found while working with it. All right, I'm seeing the thumbs up from Derek. Cool, let's keep rolling. All right. Okay, the first thing that I found that sort of completely changed it for me is Platform IO. Has anyone else heard of Platform IO? Okay, I see James got his hand up. Cool, Derek's in. Yeah, this is like necessary, I think, to do serious development with a microcontroller. So where I started about a year ago was on Arduino, and using the sort of Arduino sketch environment, which maybe you guys are used to. One of the things about Arduino is that they want you to write all of your code in exactly one file. And the more complex your project gets, the harder that is to sort of manage. So jump forward. So Platform IO is a extension that works with VS Code. So VS Code is a developer environment that's nice and lightweight and extensible. I really like it. And Platform IO gives you lots of nice things that help your project be like fully developed. So first of all, you get a file structure. Not everything has to be in one file. So if you're used to developing code and saying, oh yeah, well, I need to say this is documentation and this is a utility file, so you can keep nice structured code. Platform IO lets you do that because it knows how to compile it. And that's really, really useful for, this is a project I was doing to run a flip-dot board, which are those cool little boards that they have just a bunch of little dots that can either turn white or black. And so you can see that like, oh, well, I needed to define what the alphabet looks like so I could like, make it write letters. Excuse me. And so I was able to include an alphabet.h header file in addition to my main file. So that's really nice. Additionally, there it is. You get build management. So like I said, when you're writing this code, it compiles down to a specific processor. And so Platform IO is really good at figuring out how to talk to each of those in a way that doesn't force you to do it kind of as one-off. So you can create this .ini file, which is just a config file for Platform IO. And you can say, well, here's the board I'm using, and it does a lot of the work of figuring out exactly what it has to do to program it. And that's really nice because now if you change this, assuming that you're not using any libraries that are specific to the board, you can just say, I changed boards, which is a lot nicer. Additionally, you get dependency management. So if you're used to working in like Python, you would write a requirements.txt for Python to say, oh, I depend on all these other libraries. And that way it makes it easier to share. Or like in JavaScript, you would use like was it package.json or package, something like that. And so this is, again, really nice because your code is going to depend on other code. And so Platform.io helps you find that. It can both has repositories, and you can just write a big list of all the stuff you use. Here I'm using an RS-485 library, which is nice because why would you rewrite your own communications library? And you get unit tests, which is crazy to me. So unit testing, if you're not familiar, the idea is basically, oh, I want to write little bits of code that test my other code. And this is really, really useful as your code gets more complex. And I was surprised to see that this was even possible on embedded systems. Of course it is. Professionals have been doing this a long time. They want to be able to have robust code. But Platform.io makes it really, really easy. I haven't actually implemented these yet. I kind of started on it. It wasn't like a total walk in the park. You have to kind of like learn a lot about the testing frameworks for your specific board. But it's pretty cool that it's sort of like integrated in from the beginning. Plus you get debugging. So that's also really, really powerful. Because you can say, why isn't this working? And especially if you're doing these sort of real-time microcontroller things where you're like, I don't know, it's sort of failing, and I think it's because this, this light turned on too early or something. Debugging can actually help you see the variable state, which is super important. And I'll talk more about that in a minute. And then finally, you just get this nice little UI, which is really, really nice. Because I found working with Arduino that working with the Arduino developer environment that like, yeah, you just kind of have to click through, and I felt a little trapped in. I also did a couple other embedded systems developer environments, and it was all right. I'm sure I would just get used to it, but I found this like deeply intuitive. So you just get this little UI at the bottom of your VS Code that says, hey, check this box to compile, click this arrow to send it, click this experiment to run a test, and then just automatically open your serial, which is also really, really nice if you want to see your serial messages automatically, because it'll connect as soon as you send it. All right. Yeah, any other questions on Platform.io? Thank you for jumping in, Derek. Cool. Yeah, Debbie, this is a yeah, I don't know why it's a ini file. I think it probably stands for initialization, but it's just a config file, and it works for all kinds of microcontroller frameworks. They have really good documentation, actually. I saw Scott put the link into yeah, there you go, exactly. So yeah, you can check out the other things it works. All right. Jumping ahead, this is kind of, a general exploration. Here's a few things on C++, and those of you who are like tried and true C++ programmers will be like, yeah, obviously. But my experience was I learned it in college for a course, and then just kind of stopped writing it because like all the stuff I was writing was Python, and Python has all this support, and there was just no need. But I've really come to like a lot of it. I kind of see how its philosophy works differently than higher level programming languages. And it's pretty much necessary unless you want to try to write MicroPython to try to write something on an embedded system. So first of all, C++ is a program about memory management. I think you can get into some debates with some hardcore software engineers that, well, Rust is really about memory management. But a big thing for me was thinking, oh, well, I'm going to use code and apply it to my application, which would be a bioreactor. And you kind of have to invert your thinking here and say like, oh, the code is concerned with what the computer is doing, like where I'm putting memory. And then, I have to do that in a way that my application kind of comes out of it. But you have to think like the computer thinks. So yeah, basically what your code is doing is just saying, hey, you have a big registry of numbers, and you need to like move your numbers move those numbers through your memory and store them in specific spots. C++ does provide a lot of abstractions to make it a lot easier. but it's really, really useful for me as I was sort of like learning how to debug this stuff, to remember like, hey, if you're having a problem, think about physically where in the computer your number is currently stored. Right. And also something that an implication that falls out of that is that C++, you must define the type of thing you're storing in your variables. So, if I'm storing a string, I have to say ahead of time, hey, this is a string. If I'm storing a number, I have to say, hey, this is a number. This could be a big number or a small number. And the reason for that is that you have to know how much memory to keep open to store this thing. And it wants to be really efficient. It doesn't want to say, oh, well, I want to store the number 4. I don't need 3 megabytes of memory for that. And a nice thing about that is that because you know what the variable is going to be ahead of time, and it must be that, then you can minimize your runtime errors. So an interpreted language like Python is pretty free and easy. You can just kind of throw whatever you want into the variable, and then you may just see totally unpredictable errors because you sent it I don't know, a string, and you were expecting JSON or something. And so it's really nice that that with C++ you can get that. But you have to be really thoughtful about what you're doing. Additionally, you need to be really strict on namespaces and which things you include and how. Because there is so much scoping of what memory is available, it's really, really useful to say, okay, great. I am going to say that this variable needs to exist for the length of this function and then can disappear, because then that memory can get freed back up. Right, yeah, but if you do this, one problem that I've had in interpreted languages, and maybe some of you have had this as well, is that you kind of write 2 files that depend on each other, and so they need to import each other. But you can't really do that in a language like Python that just says, okay, well, from file A include file B, and then from file B include file A. Because they would just try to import each other forever. But the nice thing about the way C++ works is that you actually just draw from a third file that sort of declares everything ahead of time, and so you don't run into this issue, and it's really nice. And then, yeah, you just need to keep your scope tight to make sure that the data exists where you want it. So when I was first doing a lot of this, I had all these problems where I would run a function and store, the output of a calculation somewhere, and then the output wouldn't be accessible from a different function. And I sort of had to learn like, oh, yeah. By default, C++ just deletes the variable when you're not using it anymore. And so you need to be really careful about like, hey, I want you to continue to store this information for a little while, because otherwise it just wants to ruthlessly keep its memory available, which is good, because if you do that wrong, then you get what's called a memory leak, and basically your computer crashes for a seemingly unpredictable reason after X number of hours, and that number of hours can be any number. So it'll drive you totally crazy. This is working great, and then 8 hours later it just broke, and you don't know why. Oh, and then the third thing is working with strings is not great in C++, and it's good to try to avoid it. So I think clever people will be able to, write the right kind of libraries and functions to manage these really well. But by default, it's just not meant to do that. So, I'm thinking about high-level languages, your JavaScripts, your Python, and where they just make it so easy. Oh, yeah, just send some words around. Oh, step through these strings and figure out what letters are there. That stuff all can be done in C++, but the number of times I've had some garbage come back to a function. So, I'll have a little display screen, and it's just displaying like, it's supposed to write the temperature, and it'll say like temp 30, and then it just blips and says like temp $ hashtag dash dash dash, and then a bunch of blocks. So yeah, I don't know, my basic rule has been like, try not to use strings at all if you don't have to. But there is this library called the standard library in C++, and you'll have to use strings at some point probably. And so Arduino will provide you with a string class called S string, but it basically teaches you bad habits, is kind of what I've learned. It's sort of easy to get started, but then you'll end up in trouble. So C++ has this library called standard, and then you can use the string type inside of that. So that's my sort of best recommendation at this stage. All right, Andrew, did you get connected? I think I heard you.
Yeah, I figured it out. I left and came back in.
Awesome. Cool. And now I have a whole thing on real-time operating systems. We got a little time left. So any thoughts at this point? Anyone have jump in additional tips for working with strings or anything like that?
No.
All right. Okay, the other big thing is real-time operating systems. This was like a whole different way of thinking for me. I think it's really, really cool, but you gotta like, again, you really gotta think about like, what is the computer experiencing? So a real-time operating system is wait, Sing, any idea about Lua on embedding system usage compared to C++? I don't have any idea. So I've never written in Lua. I hear people talk about it. It sounds cool and interesting, but the vibe I have on it is that like, oh, it's like pretty easy to get something going. Like it has really like simple tools to sort of like kick an idea together really quick. I don't know if other people have experience with it. But it might be possible. Yeah, I see Derek, a little experience. Well, maybe we'll have to learn about Lua at one of these meetings. Okay, real-time operating systems. So a real-time operating system is one in which your calculations don't just depend on logical correctness, but on the time the calculation was done. Like it matters when something happens. So this is an example. Usually I don't tend to pick military missile examples, but this was, I thought, fairly clear, and I found it online. So you can imagine you have some computer that is taking a measurement about where it thinks a plane is, and then it wants to try to shoot a missile at it. Well, the time that it calculates matters a lot because that plane will keep moving and it's going to try to estimate where the plane will be by the time the missile shoots. And so it has to be very aware of time. And so it could make a correct calculation for where this plane is in this moment. But if the time changes in some way, then that won't be true anymore. So that's the kind of abstract. What it often means in practice for a microcontroller is that you have one processor which can do one thing at a time. Most laptops and phones and stuff now have multiple processors, and there's some deep magic that handles a lot of that. But if you have one processor, say you just have a really cheap, simple microcontroller, you basically have a meta process that is deciding what work to work on if you need to do two things at once. So like an example for me is, oh, I want to measure a temperature, and then I also want to send that temperature value over the network so that someone knows what temperature it is. And that someone could be anything. And so great, now I have thread 1 that measures my temperature and thread 2 that does the sending. And so what happens in a multi-threaded process is the first thing will get worked on, and if that work finishes, great. And then now the sending can happen. And if that work finishes, great. And then it'll measure again. And then say here in block B, if we started to send off that data, but you wanted to take another measurement, then the sort of meta process can figure out, oh, no, stop trying to send the data for a second because I have to take this measurement. And in that way, you can keep that real-time thing happening because the processes that need to happen exactly when they need to happen. And so you can sort of break up your calculations like this. So I think you can kind of see that like this implies a sort of limit because eventually all of these blocks will be filled and the processor won't have any more time. And so you have to be aware of that. Yes, okay. Here's the thing, the processor goes really fast, so it like feels parallel, but it's not parallel. And that becomes important when you're coding it. So here's a rather, sort of complex diagram that mostly you can kind of work through on your own. I find it's fairly intuitive usually, but I need to kind of stare at these things for a minute to like get my head around it. But essentially, if you have two threads, so I have my temperature measuring thread and my temperature reporting thread, they have to signal to each other when to wait for the other one to finish. So I don't want to report a temperature until the temperature has been measured. When to go. So as soon as the temperature is measured, I should send it off. And also when a shared resource is locked. So the actual memory value where I'm storing my temperature. So there's some silicon inside my microcontroller that is keeping track of like the number 30 when is that available? So if I'm writing to it with my measurement and then I start to read it halfway through, because remember, these calculations can be interrupted, there's just going to be garbage inside of that memory address. And so when I'm writing my memory, I have to say, hey, I'm using this memory address right now. And then when my network reporting thread can say, oh, now it's become unlocked, I can now read it. And so you can kind of see on the right here, this sort of vague idea. If you have something like a controller thread and a worker thread, um, the first thing that might happen is the controller thread creates another thread, and then it waits. And it just says, oh, I don't need to do anything until my worker thread is initialized. And it just kind of sits there. And then it's the worker thread's job to send a signal back. So they call this a semaphore in a lot of this. And then that says, okay, you don't need to wait anymore. And then they both start to do other things. And you can see they have start and stops baked in here. Does that basically make sense to people? Cool. Okay, so let's go back to sort of the practical reality. I think I'm probably the last person who should be teaching a course on multi-threading theory, but hopefully that gave a strong enough grounding. So how have I worked with this? I've been using FreeRTOS, which is a free and open source real-time operating system that's for microcontrollers. It's platform agnostic. It theoretically has good documentation, although what I found is that you'll read the documentation 6 times and be like, wait, so how do I use this? So it's sort of like there's a lot of it. It's at least partially supported by Amazon. Thank you, Scott. Again, gosh, excuse me. It theoretically is well supported, but I don't know, I've had some problems with it. But it's open source, it's free, and you can at least find some things about it. Oftentimes the sort of microcontroller world can be pretty locked down or hard to find things about. Okay, so how do you actually implement that? Well, this is just a little bit of code. If you're familiar with coding on Arduino, this might be how you do a single thread. So you have a setup function that says, hey, when the microcontroller starts, run this function. And then you have a loop function, which says, just kind of keep doing this forever in a big loop. And so you can see what this does is, okay, I want you to begin my serial connection and then initialize some variable to 0. There's probably some bug in this code. It's barely anything, but I never underestimate my ability to create bugs in a C++ code. And then you just say, okay, well, I'm just going to add 1 to k, and then I'm going to print k to my serial, and then wait 500 milliseconds, and then do that forever. Well, this wouldn't work in a multi-threaded setup because this delay function will actually stop the processor. It won't do anything else for 500 milliseconds, and then it loops. So if you wanted to be doing something else, like taking a measurement in the background, the processor wouldn't be capable of doing that. In FreeRTOS, you do it a little like this. And again, this is some real pseudocode, but essentially you keep your setup function. And then inside of that, and remember, because I'm using Platform IO, I can create additional files that have functions defined, like init my serial connection, init my Wi-Fi, init my LEDs. Initialize is what I mean by that. So maybe I call some initialization functions, and then I use this function called xtask create pin to core, and give it a bunch of functions. And I basically just say, hey, I want to make a new thread. So I'm gonna the thread will run this function called keep Wi-Fi alive. We'll look at that in a minute. I'm going to call it keep Wi-Fi alive. I'm going to allocate this much memory to it. I actually forget what this null function does. And then I set a priority. So if one task says, I really need to be run right now, and there's only one processor, the lower priority will get run instead of the higher priority one. So here I'm saying it's more important to me to keep my Wi-Fi alive than to blink my LEDs. And then I keep a handle object. Excuse me. So here I've created 2 tasks. One that says, hey, I just want you to always make sure my Wi-Fi is connected. And then the other one is going to blink some LEDs. And then after that setup goes, I'll create these tasks. That'll start to run in the background. And then I just say, okay, now start running this loop. And you can see there's nothing inside of it. And that's because this is our idle loop. So this is just what the processor does when it's not doing anything else. And so if you put stuff in this, it's sort of unpredictable, what will happen. So all the best practices I've seen say, yeah, leave that empty. Okay, so then, great, now I've created these threads. What are the threads? Well, if I use this blink LEDs thread, I would define a function called blink LEDs. So you can see I've referenced it up here. And and I've said, yeah, it takes this void star parameters, so I'm allowed to send it parameters. In this case, I'm not. Um, and then it works kind of a similar way. There's a setup function. So the first thing it does is it'll initialize a variable called current and set it equal to 0. And then it runs this for loop. And you'll notice about this for loop that it's infinite because it just 2 semicolons. So it has no rule about when it's supposed to finish. So it just loops forever. And that's good because FreeRTOS throws an error if you ever leave a loop. Like these functions aren't allowed to end because they're just supposed to be infinite tasks. They are allowed to delete themselves. So that works, but you can't just end the function. It like won't know what to do and the whole thing will crash. And so you can see here, all this does is just says, okay, great. Current equals 1 minus current. So in this case, current is 0. So I'll get 1 minus 0 is 1. And I said, is current true? Oh, yeah, it is true. Okay, great. Well, now I'm going to set my LED to on. So we can imagine I'm using some library that lets me turn an LED on and off with set and clear. And then I'll jump down to this thing called V task delay. This is another like crucial part of the way the RTOS stuff works. Where you remember I had a delay function earlier, and that was going to completely block the processor. The processor wouldn't be allowed to do anything else. The task delay actually says, yeah, you can just go do something else. So here for 1,000 milliseconds, and so you can see I'm dividing by port tick period ms, and that's because processor speeds may be different. So we can actually play and fine tune with how fast the processor ticks across. In this case, this value is 1. So 1 millisecond is 1 quote unquote tick of the processor. So 1,000 divided by 1 is just going to be 1,000 milliseconds, which is 1 second. So basically it just says, great, now that I've run this code, I'm just going to sit and wait here for one second. And then as soon as that's done, I'll hit my loop and I'll loop again. And now my current will have flip-flopped, so I will instead turn the LED off. So the outcome of this would be a blinking LED once per second. And this is really nice because I can be doing all kinds of other things. The processor is completely freed up during this time. So that's really high level on FreeRTOS. Any thoughts or questions on that? Anybody know any tips or tricks? There's a bunch more functions here. It's actually pretty cool. But I think probably for this stage, it doesn't make sense to get into some of the weeds on it. All right. Cool, home stretch, just a couple more things. I didn't know you could live debug microcontrollers. I was sitting here being like, I don't know, I just got to write serial prints to my controller all day long. But of course, in the 80s, they invented a bunch of different debugging protocols. And here's just 2 options. This white box here is called an Atmel ICE. Atmel is a microcontroller manufacturer. And you can see basically you stick one end to a USB, which is on the back of it, and then the other end it'll vary by boards. The boards have to expose special pins or pads that say I am for debugging. But if they have that, then you can just sort of connect a ribbon cable like this to the correct pads. And then it knows how to debug. So the board will constantly be reporting its memory state back to your device. So if you're using Platform IO, it just works like a debugger. It's so great. You really just like say, oh yeah, I want a breakpoint here and I can check my variable state. Oh, that's what's going wrong. Oh, okay. This thing is $150. It's a little pricey, but you know, it is sort of nice. It has some good bells and whistles. On the other hand, there's this ESP Prog, which I've also been playing with, that it's like $20. And you know, usually you have to order them on Alibaba or something. They're kind of coming out of the sort of like Shenzhen fabs. But that's like super cheap. It's great. And it works with most ESP32 boards, which is really nice. Because if you're using ESP32, that's a pretty broad ecosystem. And again, it varies by board. You can see in this case, they've had to get the debug pins by putting pins on certain of the GPIO pins. So the downside of this would be you can't use those pins for other things if you want to debug on them. But that's really nice as well. So yeah, if you're using kind of one of these SAM boards, I think really any of the ARM Cortex boards, the ML ICE is compatible. And then for ESP32, you can use the ESP Prog. Kobe, do I now primarily use FreeRTOS over Arduino code for your projects? I do, yes. So it's definitely still faster to like, if you just want to make an LED blink, it's still faster to just like, you know, the Arduino IDE is so easy. Like you just start it, and you pretty much can have something on a microcontroller in 2 minutes. Especially because they have all those examples. Um, but for anything that's like a project, I really really like the Platform IO environment. It like feels like a coding environment. I always feel with the Arduino IDE that I'm just like I'm short a few tools. Whereas the Platform IO is really nice. And for FreeRTOS specifically, yeah, there's definitely some really really dumb examples where it like kind of doesn't matter. Like I think I mentioned that flip dot board, which is like totally just like a for fun art project, and like it really just needs to do one thing. Like it needs to uh, change the flip dot boards, and I don't really care about concurrency on that. It's not a real time system, quote unquote. Um, so for that, I might skip it, just because it's a little bit of setup. But I really like all the tooling that comes with FreeRTOS, and like having already kind of started to think that way, I found it's easier to kind of keep thinking that way. And also the delay thing is so great because you're constantly when you're programming microcontrollers, and when I was doing hobbyist stuff years ago, even you're constantly having this problem where you realize, oh yeah, I need this to wait 1 second, but then I can't, like, now it's not responsive. Like if I want to press a button, I can't it won't respond to the button until it's finished waiting 1 second. And so I really like the tooling for that. One thing I didn't mention is FreeRTOS also supports interrupts. So like you can have a button be instantaneously responsive instead of having to wait for the code to get to that point. Um, so I just have one more slide here, which is I've just kind of come to really like this design pattern. So I just kind of wanted to pitch it out to you guys, which is to say, great, let's make these sort of compute objects, these little microcontroller devices that just kind of like live out in the world doing stuff. So they're in the lab and they're taking measurements, or it's a little box that you press a button, kind of like we saw last month with Anthony Oreshkov's pack cell volume machine. Yeah, it's just like a little thing, and it just like does one thing well. And then that can stream information to some kind of supervising device. And so that you can write in a higher level language, and that'll give you a lot of the tools around, managing complexity and sort of the modern internet tools if you want to use those. And so you can use a streaming protocol. You could use all kinds of communications protocols. But I've come to like MQTT pretty well. It's nice and lightweight. We talked about that a little bit with Matt Fay's Sparkplug B talk 2 months ago, I think that was. Another one that is fairly popular is OPC UA. So that's perfectly fine. I have no issues with that. And then from there, if you want to interact with it, then you talk over a web API to that supervising device. And this is nice because you're not like hacking around building, little garbage interfaces when you could just use like, oh, let me just use kind of a plug and play web framework that's like has buttons and uses all the sort of modern internet tooling. So I've really come to like this sort of design pattern, and I wanted to just sort of pitch it out to you guys here as well, because it lets each part do the thing it's good at. The microcontroller can just like take the measurements and stream the data, and the supervising device can like think at a high level about like device management, and then you can have websites that like just provide an interface and like are cool and polished and do the things you want. So that's kind of where I've come to on it. All right, let me sum up. I know this is kind of just a whirlwind tour, but basically, I like using microcontrollers to turn objects into compute objects. And they're great if you need something that's small, it does one thing forever, and it's just like highly configurable. So you really want all of the tools in front of you. So instead of buying let's just say it's an Opentrons, right? I always pick on them because I like them. But Opentrons it's a tool, and if you have liquid handling, that's probably a good fit. If you have something much more complicated that you need to do and like no one else is doing it, then the microcontroller is probably for you, because it just gives you all of this tooling, and like there's a huge amount of ecosystem around it. And I think that was literally everything I had. Yeah, it was. All right. Do I use a pre-built IoT service like AWS IoT, or you have your own? I've been playing around with it myself. So I think IoT, one of the things I found is that like the IoT world really imagines what you're doing is deploying 5 million sensors across the state of Kansas. And so there's a lot of services that are just like, oh yeah, you can just call up to us and we'll manage all your data. and it's low power and uses a mobile LTE signal and like has lots of great things that aren't really that useful if you're doing lab automation. So me personally, I have been sort of skipping the AWS IoT kind of approach because it's not so hard to build the stuff I want in-house. That said, looking at it, it does seem like it's really nice for a lot of applications, especially if what your goal is to just get a gobs of data in. I have to do kind of a little more logic for like data storage stuff. Um, and yeah, and so I don't know. For me, it was easier to just kind of roll my own server, but yeah, as near as I can tell, they're like pretty easy to work with if you want to pay a little bit of money. All the DevOps people I talk to basically say, yeah, it's probably a wash cost wise. Like you're gonna pay for it one way or the other. But if you don't want to do all the maintenance and support and learn how to do all this extra stuff, then I think the cloud services are a pretty nice solution. Um, okay, yeah, Derek had to run. See you, Derek. Cool. Yeah, we're at time. I know that went a little long, but hopefully it was interesting. I don't know if anyone has any sort of closing thoughts or any more questions. I have a little time. Can stick around.
What are you actually using it for
Yeah.
yourself?
So me specifically, the bulk of the work was really about bioreactor firmware. So like what is gonna run this bioreactor? Um, and the trick with bioreactors is you want them to run many days and you want them to be highly reliable. And so the microcontroller seemed like a good solution. Maybe you kind of heard earlier, I sort of go back and forth like, I don't know, a Raspberry Pi could basically do this. Um, but I've kind of stuck with that design pattern I was talking about that says like, make the bioreactor do the thing it does really, really good. And then it streams its data out to some sort of higher level management server. So we kind of have a split mode there. But the cool thing about kind of having developed, the sort of core of what we've developed here at my company is, yeah, it's a thing that takes measurements and streams the data, which you can use all over the place. So we've actually found it's kind of useful because these chips are cheap and small. Like sometimes we just have a one-off application. Like we had to test a bunch of DO probes, dissolved oxygen, and the easiest thing to do for us because we've already done the work was, oh, just grab a chip and plug it in. This thing talks over RS-45, which is a communications protocol, and great, we know how to read that. And so now we just had a device and it was streaming data into a database from our DO probes, and that helped our probe scientist who was trying to figure it out. Like he just kind of didn't have a way to get that data collected so he could do calibrations, and because we could just kind of plug this thing and turn it on and it would start, then he could just kind of grab all his data from the database and away he goes. So sort of a general purpose, but yeah, mostly it sort of came out of the bioreactors. Any other thoughts or questions? Thanks for shouting in the chat.
Is your bioreactor open source, or is it going to be a commercial product?
It's going to be a commercial product, but the exact thing that means is sort of up for grabs. So I think there's a lot of possibilities for open sourcing parts of it such that it is sort of useful. And my sort of belief is that there's this whole sort of set of people who are really interested in working on bioreactors, or working on really any automation stuff, and creating this sort of ecosystem and community. And that's us, right? That's people like Open Auto Club. And it's not like they were going to buy a $100,000 bioreactor anyway. Not that ours is going to cost $100,000. So we're figuring that out. What I've learned is that when you start a startup, the exact go-to market changes a lot, and there's a lot of things you learn along the way. Generally speaking, what we're doing here at this company is it's called Biosphere, is mostly focused on the process itself. So we're building the bioreactor so that we have a good bioreactor to work with. So it's not really, immediately like, well, how do we sell this thing? But I think that could be a good path. So we just have to figure it out. And get the capacity, because like actually it's one thing to kind of, I mean, you guys know this, it's one thing to make something that's kind of janky but it works and you know how to use it, you know its quirks, and it's something entirely different to make a commercial hardware product that like always works and can be served. So that would take like additional support staff. I mean, all the legacy lab manufacturers, more than half of their staff I think is about support and sales than the actual design. All right. Any other questions?
I think I can share some thought on bioreactor
Please.
because I think because we have talked like bioreactor idea before, and after our biolab need to like rising, for example, such as slime mold, and I find that if we working beside the model organism, there are more possibility and more necessary to modify our cultural environment. So I think to like have more skill set on building this kind of the maybe organism specific bioreactor environment is very will be more important in the future for this kind of the company. For example, like Slimo, they afraid of the light, and they have the different phase of the life stage. This kind of the organism right now, I think they have no device such as bioreactor designed for them. So if I am the startup, I have to like customize my bioreactor environment. And currently, I think most of the bioreactor in the market is working like for the traditional model organism such as yeast, E. coli, and so they decide like working in the fluid environment and shaking. But I think right now more people working on non-model organism. This kind of the need for the customized cultural environment and sensing system, I think will be quite important in the future. Yeah, some thought on this, like right now we only see one kind of the bioreactor in the market, but in the future, I guess there will be a kind of the large ecosystem on this kind of the flexible design parts in this kind of system. Yeah, some thought on these things.
Yeah, I think you're exactly right, Wei Ting. The big thing for me was sort of just realizing that, like, oh, well, what you care about is the cellular environment. That's as big a part of what happens with the cell as the DNA is. So you have to figure out how to provide the right environment. And like you say, if we just say a bioreactor looks like one thing, well, then you're going to get one kind of result. So yeah, I totally agree. One thing, I mean, that might be interesting for Open Auto Club is I've discovered bioreactors are really expensive. And if you do the costs on it, it's all the probes. Like it's actually the measurement that's really expensive. You can, especially if you're going to use like an antibiotic or something like that, like the standards are really low for a bioreactor. You can use a mason jar, but the probes can be really expensive if you want good, reliable probes. So I don't know, that's something I think for people like us to work out and make better, because ideally, if you want different kinds of bioreactors for different kinds of organisms, well, they have to be a lot cheaper because you have to be able to try stuff. And so that, hackers can play around with it.
Have you found any secrets to pro pricing?
Pro pricing? Well, what
Yeah.
do you mean pro pricing?
A pH sensor, O2 sensor. I mean, if that's the bottleneck of making these things cheaper, is there any kind of cutting edge research, biological sensors, cell-free, biologics that change color? I don't know. I'm just thinking like outside of the box.
Yeah. I mean, so my favorite is and always will be this sort of optogenetics stuff, which is, essentially, you have some kind of sensor that measures something, some color produced by the microbe, and then you can then put light back into the bioreactor. And if you have a gene that responds to, say, a blue light, then you can sort of directly regulate genes that way. That's pretty cutting edge. I don't know anyone who's using it in a sort of practical sense. They're just sort of studying it. Otherwise, yeah, like you can get probes for like a pH probe for, I don't know, 60, 70 bucks.
But the idea is $5, right? That's the holy grail.
Well, here's the other thing. Those probes can't be autoclaved. Like maybe they can. So if you actually want them to be sterile, like you actually end up around $1,000 for these things, and it's pretty hard to get lower. The only other solutions would be IR probes, NIR probes, any kind of optical probe, and you could try to tune it for the exact molecule you want to measure, but it's not as reliable as like, hey, this is the probe that's been used for 20 years and it's perfect for measuring oxygen. So I think you just have to have a really strong understanding of your requirements.
Well, I think, economics of scale, right? If everyone had a bioreactor at their house, just like the magnetron, how they went from, radar detection to our microwave, it went from thousands of dollars per unit to $2. That's the gimmick, economics of scale. If I have to figure out how to make this $2,000 autoclavable, pH scale, I can, if I got to sell 100 million of them, I definitely can figure out a way to make them cheaper.
Yeah.
I mean, look at cell phone cameras. I mean, just the sheer volume, I can put a camera in anything now for pennies on the dollar.
Yeah. Yeah, no, totally. I think sort of consumerization of this technologies will make it necessarily dirt cheap. The cameras are so cheap and they're so good. Like you can buy a $2 camera that you just plug into your microcontroller and it's really good. Anyway, guys, I have to run. Any kind of closing thoughts? Anyone have anything they want to slip in there?
I think I feeding back to James' idea. Right now, like for example, we measurement the pH value in the kombucha. We use the pH sticker. So maybe can combine these two of idea like camera and the chip measurement sticker. Maybe this is some kind of idea can roll the price, like combine the traditional chip like paper-based measurement tool and the camera, and people can like shift the paper-based sticky, and you just provide low cost of camera and the software.
What about a non-pathogenic, organism that produces that cabbage protein that you just have it in your bioreactor, and then you just look at the color, it's green, it's good, if it changes colors, because I can make, a digital, camera sensor that measure color in real time. And then, I don't know.
No, I like it. Maybe we should do just like a probes brainstorm. I think it would probably be really useful. And I definitely think imaging is a good path to go down because there's so much technology around it. All right, guys, I have to run.
Thanks, everyone.
See you, Scott. See you, James. See you, Paul. Bye, Jenny. See you, Daryl. Bye, Wei Ting.
Bye-bye.
Bye, good to see you all.